Thank you very much. Yeah, so most of this talk is going to be based on it. Towards the end, so I have just recently started a 5-year fellowship, so based around accelerating SPH as well. So I'll have about 15 minutes on this part, and then sort of five minutes introducing sort of what my work is now. So I should say this work was done a few years ago while I was in the SPH Manchester group. Okay, so well, I guess I don't really need to explain why fluid structure interactions are important, but they do obviously govern lots of engineering and natural phenomena throughout the world. However, they're very difficult to model, they're very difficult to analyze, and the physics is difficult to it's a challenge to understand the different types of physics going on as well. When we model them, we have to think about multi-physics, how to couple at the interface. We have to deal with deforming domains in terms of the physics. We have different sound speeds, different dynamical instabilities that may occur as well. So there's lots of things to think about. Because they're so difficult to model, quite a lot of the times, people will introduce some form of reduced order modeling. So you're looking at sort of dense arrays of structures. A very sort of classic simplifying assumption to make is to introduce a porous model. However, the price you pay for sort of making those assumptions can sometimes lead to not properly capturing the correct physics. So this is the sort of motivation behind this work. So sort of high fidelity modeling of fluid structure interactions that capture the physics that we want. Okay, so I'm going to talk a bit about now how we actually model this. So first, very quick introduction to fluid modeling with SPH. I probably don't need to go into too much detail here, but the two main equations for Lagrangian weakly compressible SPH are the conservation of mass and the conservation of momentum as well. Usually when we talk about fluids, we'll split the Cauchy stress into an isotropic pressure term and a deviatoric viscous term, couple them together via an equation of states, and then apply our normal SPH operators to get our derivatives. Okay, so that's a very brief introduction to fluid modeling with SPH. Now, for the structural modeling, we actually did decide to use SPH for that as well. The sort of two main reasons behind that are because we're using SPH to model fluid. It's going to be easier to integrate a structural model into DualSPHysics if we use SPH for the structure too. Something that's also sort of been touched on a bit as well is when you work with a monolithic scheme for certain classes of FSI problems, particularly when you have mass ratios close to 1. Monolithic schemes provide enhanced stability over partition approaches. Usually with partition approaches, as has already been mentioned, you have to introduce some strongly coupled scheme. So how do we do it with SPH? Well, if we go back to our momentum equation here, which is valid for any continuum, not just fluid. One way to do it is to split the Cauchy stress again into an isotropic and deviatoric part, modify the equation of state so it captures the physics of the constitutive model, and then just solve it like we did before. It sort of semi-works. It's quite unstable, and there's sort of three main issues with how this works. So tensile instability, linear inconsistency, and rank deficiency as well. So I'll talk a bit about how we overcame those. So tensile instability basically happens because of the shape of the smoothing kernel. It's a problem for fluids, but it's an even bigger problem when it comes to modeling structures, and you end up with this sort of particle clumping that can ruin the solution. One approach to eliminating that with structural mechanics is to reformulate the problem in terms of the total Lagrangian approach. So now everything's reformulated with respect to the initial configuration. So we start with our original momentum equation, we now end up with that. It's the exact same equation, solving the same physics, but just in a different reference frame. So all of our quantities, our initial quantities, all our operators are measured with respect to the initial configuration. Again, from here, we can just apply our normal SPH discretization, and it completely eliminates the tensile instability. A sort of added bonus to that is that because everything's measured with respect to the initial configuration, we don't need to recompute the neighbors because it's just the initial set of neighbors that we had. We don't need to recompute kernel derivatives because it's just the initial kernel derivatives that we had. We don't need to compute the continuity equation because we're just working with the initial density. And so actually it's more efficient as well. There's less work to do. The second issue is linear inconsistency. So this happens because at the boundaries, you don't have a full set of particles within your kernel support. When modeling fluids, this is the sort of way that we usually get around this is we add extra layers to the boundaries, but we can't do that with structures because that changes the geometry. So all we do here, which is not a new technique that's been around for a while, is we introduce a kernel correction that allows us to recover the gradient of a linear field. And then the final issue is rank deficiency. So this occurs because of the collocated nature of SPH, where you have velocities and stresses defined in the same location. What this means is that your deformation gradient tensor is not unique to the particle arrangement. So you can have two different particle arrangements that both give the same deformation gradient tensor, therefore give the same stress, which therefore means that there's no stiffness to stop those two modes occurring. So those modes can be excited without any actual energy added to the system. This happens also in reduced order elements in FEM, which is why it's called where it's called hourglassing. So if you have a Q4 element here with just one integration point in the middle, you pull it apart at the top, squash it at the bottom. Obviously that's deformed now, but if you just have one stress integration point, that's going to measure zero stress. And yeah, so both those modes can then happen without any input. So the way around this is to, well, one approach is to introduce stress integration points, but that's where you define some particles have the velocity and some particles contain your stress. That's quite hard to do in general for 3D geometries, and it also effectively halves your resolution too. So what we ended up doing was introducing a penalty force, which penalizes any deformation that's not exactly described by the deformation gradient tensor. This is easy to implement, it's efficient. The downside is it does slightly modify the effective stiffness, so you've got to use it sparingly. And it also does introduce an additional tuning parameter as well, which is not ideal. So what we end up with after we apply the SPH discretization, this is our momentum equation now. We have our first particle Kirchhoff stress, we have the kernel correction plus the penalty force term. And then through our constitutive model, we can go from the deformation gradient tensor F at the bottom here up to our first particle Kirchhoff stress tensor. Okay, so that's the structural modeling. In terms of the coupling, so we just use the sort of very basic pre-existing boundary condition in DualSPHysics, which is called the dynamic boundary condition. The way this works is for boundary particles, you evolve the continuity equation as normal, but when it comes to the momentum equation, you don't do anything because there is no acceleration, or if there is, it's prescribed by the modeling. So in terms of how we adapt this to the fluid structure coupling, we introduce a third particle type, which is for our structure particles. For the fluid, they see these structure particles just like a normal boundary particle, except now it has a velocity. And then going the other way, the structure sees the fluid particles just like a dynamic boundary particle would see the fluid too. The only difference now is we do integrate the momentum equation for the structure particles. Like I said, it's quite a basic boundary condition. It's not the most accurate, but it's easy to implement, it's efficient, and it doesn't require any geometric information about the boundary as well. So works quite generally. So putting everything together in terms of calculating the acceleration for a particular particle, we basically just sum up the contributions from neighboring fluid structure and boundary particles. So for the fluid particle here, it's just the same. I've dropped the viscous term just to fit everything on, but I've split the terms from each of those particles. For the structure particle, this is the contribution from the fluid, but then for the structure and the boundary particles, we now have this total Lagrangian form. Okay, yeah, so that's it. So just to talk briefly, go through the validation that we've done for this. So testing the structure just on its own. This is quite a popular benchmark case. It's just a clamp beam oscillating under its own weight. Like you can see, we can get very good agreement with the benchmark FEM results and convergence towards the benchmark solution as well. Now for the full FSI, so this is the same benchmark, a flexible beam attached to a rigid cylinder, Reynolds 100, so you get vortex shedding, which interacts with the flexible beam, and then you get this self-sustaining flapping motion. Again, very good agreement with the benchmark case. What's quite nice about this is that to get this to work, you have to sort of use quite a lot of the bells and whistles that come with DualSPHysics. So we have the inlet boundary condition, which is fairly novel for SPH. We have particle shifting to stop voids forming in the vortex shedding. And I think as well we have the new and improved modified dynamic boundary condition for the channel walls as well. So it's nice to sort of demonstrate that it works with the other capability that's in DualSPHysics. In terms of violent free surface flows, we want to demonstrate that as well. So on the left-hand side, all the natural frequencies are aligned with each other, so you have this sort of nice regular waving motion. On the right-hand side, it's deliberately misaligned with the sloshing in the natural frequency of the structure, so you get this sort of chaotic motion. Generally good agreement with the benchmark data. The right-hand side case, obviously there's some dispersion in the literature because it's chaotic, but generally good agreement. And then finally, just demonstrate that it works in 3D as well. So this, as far as I'm aware, this is the first time this case has been done in 3D numerically. Fairly good agreement. There is a bit where you see that sort of dip, where we're not following the experimental data, the sort of kickback. There was another group that did some 2D work using, so here we're only doing single phase, we're not modeling the air. What they showed is that you need to model the air to get this entrainment part right here. But obviously in 3D, that's massively expensive. Okay, so just to kind of quickly summarize that. So the sort of main aim here is to develop a fluid structure interaction model that works for violent free surface flows and flexible structures. This is based on a unified SPH framework, so we're using SPH for the fluid and the structure as well. And it's sort of validated against a range of different cases. It is in the latest release of DualSPHysics, version 5.2. If you think it's if you think you can use it for your own work, please go ahead. And if you have any questions using it, need help setting up a case or anything like that, please just get in touch. I'm always happy to help with that sort of thing. Okay, so just to sort of briefly go through what I'm working on now. So the FSI stuff was a few years ago. I've just started a 5-year fellowship working on sort of ways to accelerate SPH. Why we want to do that? So obviously, real world problems involve sort of large spatial and temporal scales. But also for typical design workflows where we're doing optimization, uncertainty quantification, these require many simulations. So it'd be great if we can find ways to actually try and accelerate this. Advances in compute have helped a lot, especially GPUs. I'm not sure where SPH would be without GPUs, but there is always a limit to how far that can go. Particularly if we talk about strong scaling. So how else can we accelerate SPH? So there's a few ways sort of planned. One way which sort of follows on from the previous talk is using graph neural networks as a low fidelity sort of coarse-grained surrogate model for SPH. So I won't go into too much detail here, as the sort of previous talk went into quite a lot of detail here. It's actually nice to sort of see their work. I was aware they were working with convolutional neural networks, but the graph stuff I wasn't aware of, so maybe there's some scope there for collaboration. But the sort of key point here is that particle-based simulations can pretty much be described as message passing on a graph. So there's some real structural similarities there between graph neural networks and SPH and other particle methods. There's been some proof of concept studies so far, not a huge amount of sort of what I call quantitative validation. There was a slide very similar to this in the previous talk, but the sort of key point that I wanted to sort of raise, which is this message passing layer, which is the sort of workhorse in graph neural networks, is very similar to the SPH convolution. So you have this edge update here, which is some function of the edge features, so the distance and the two nodes that connect the edge, and then you have this aggregation part too. So if you combine the edge update and the aggregation, that's exactly the same as the SPH convolution operator. So there's some real sort of structural similarities there. Sort of slightly different to the previous talk, rather than just solving the PP here, we're looking at solving the entire right-hand side of the momentum equation. Like I said, I actually only started this work a few weeks ago, so very sort of rough, very sort of initial stages. But the first thing was to reproduce some earlier work. So there's a data set generated from a material point method solver from a group at DeepMind. So they train on the accelerations for a single time step. Once you have your accelerations, you can integrate that in time as normal. But then what you do find is that even over long time trajectories, at least qualitatively, it seems to work semi-okay. Like I said, there's not really any quantitative validation here. So that's sort of a key part of what I want to do. Something else I mentioned, you can encode the particle type, so you can introduce boundaries. Because you're learning the interactions at the particle scale, it does seem to generalize quite well to different particle resolutions and different geometries as well. So next steps going forward, like I said, this is sort of in the last few weeks. Next steps going forward, I'd like to generate my own data set with an SPH solver. Look at some proper quantitative validation, as well as performance benchmarking and integrating with DualSPHysics. So just to kind of pick up on a question that went for the previous talk, which was about can we replace machine learning? Can we replace SPH with machine learning? That's not really where I see this work going. So I think my own personal opinion is that it should complement, but not replace. So the two main ideas that I have are around accelerating single simulations. So Low fidelity models will enable sort of novel multi-fidelity parallel and time strategies. Hammer wheel, which is one of the most popular parallel and time methods, actually requires this low fidelity model to do the serial prediction first, and then you start your high fidelity SPH from initial conditions based on that. There's some unique challenges posed by particle method. I think maybe some of the stuff that Stephen presented earlier could help here. And then the other approach, the other sort of arm that I see is accelerating large campaigns. So sort of what I would call targeted fidelity. So if we require lots of simulations for optimization or uncertainty quantification, you want to build a surrogate model of your parameter space. Do you run a handful of high fidelity stuff, or do you run thousands of low fidelity stuff? There are ways that you can actually combine data from multiple sources. So this is not my work. This is from a group in Manchester looking at RANS and LES data. You can do it with a neural network, but actually they also did it with Gaussian processes. And when you do it that way, you also get quantification of the uncertainty there as well. So with that can be fed directly into existing optimization and uncertainty quantification techniques. And then that's it. So yeah, just to say thank you to people involved in this. So obviously the group at Manchester and the group at Legal as well. Yeah.
Thanks, Jay. So do we have any questions from the audience here? Are there any questions online as well? No?
Yeah.
Just to get your idea, actually, you use dynamic boundary condition. What do you think about using MDBC for these cases?
Yeah, it's
dynamic.
Yeah. So it's been on my to-do list for a while. I actually started looking into it again just this past week. So maybe in the future, because you're right, it'd definitely be good to have. And I hopefully don't think it'd be too much extra work to do that. But yeah.
Probably follow on. So just my own understanding then. You're effectively pulling the boundary out of the solid. Is that right? So is there a boundary at the intersection?
So they're just sort of normal dynamic boundary particles.
Yeah. So you're effectively defining a DDC on the intersection.
Yeah.
So if you want to put the NDDs, you have to recalculate.
You do need the normals then.
So every time the boundary particle you recalculate.
Yeah, but you should be able to get that from the deformation gradient tensor. You have to do like a polar decomposition, which I just realized this week is actually not as simple as what it sounds, but it is possible to do that. There are other ways to track normals as well, but probably that's the most mathematically rigorous.
So if that's the way you're doing things, do you need the particles apart from completing do you need the particles inside? So if you have something complicated, so let's say we've got to Stanford bucket, would you need to actually have any particles on the inside, or would you literally have a shell of the bunny?
You could have, yeah. In terms of geometry, the structural model is fairly general.
Yeah.
The challenge is stuff like constraints and stuff aren't that general. Really, at the moment, it can be free, although that's not really tested, or it can be clamped. That's all where we are.
Yeah, very nice, thanks, John. If you don't mind, on your fellowship on the neural network stuff, on the parallel and time stuff, From what I gather, you're not really fixed on SPH in a particular approach either. Is it got fair to say? Are you going to look at general particle methods for this?
What was that, sorry?
Are you going to look at general particle methods?
No, well, so the plan is SPH, but I don't see really any restriction. I mean, although I haven't mentioned it, part of the fellowship is in collaboration with the School of Engineering at Edinburgh towards like offshore renewable stuff. So I'd say SPH will sort of feature heavily.
So on the parallel and time stuff, so I guess something like SPH is in the law that will do initialization. And then you mentioned the high fidelity technique to sort of fill in the gaps, I guess.
Yeah.
So what do you think there in terms of scheme?
Well, so again, it's quite general, but the idea that I had was for well, at least in my head, is using the GNMs for the fast serial part, and then starting multiple SPH from the GNM part. So because at least, so this is what I mean about not being able to replace SPH with machine learning. I think we have to accept, well, maybe in the future, but accept the fact that it's a low fidelity model. It's not going to be as accurate as SPH, but it can still provide benefit by being much faster. So.
Okay. Yeah, in my mind, I went straight to sort of high order schemes, you know, like spectral methods and that sort of thing. And then I guess if you care about offshore and high performing wave dynamics and restricted kind of spectrum. So,
Yeah.
Yeah.
I think I'm reading a bit slow to make connections, but so the parallel time stuff, something that people can do with finite volume methods is have a mesh that exists in space and time. So basically X, Y, T, or X, Y, Z, T. So that when you're doing finite volume, you can have all of your connectivity changing in time. So it allows you to do like arbitrary motion and those sorts of things. It's not very common to do that. But one of the other things it does allow is parallelism in time if you want to. Because I mean, instead of having a moving performing grid, you've got a single grid, which is then enormous. That's one problem.
Yeah.
You can then essentially, if you're marching in whatever tracing variable, you can march the whole grid. So within reason, you can parallelize it. You can do a similar thing in SPH. So you kind of each particle is following a line through X, Y, Z, T, and you have a scope. Possible, I'm not trying to do it. There's conceivable, you've done that. You could solve those trajectories through X, Y, Z, T. That's lower fidelity and then refine it. So I don't know, almost having my SPH at lower resolution through the full time history, and then it gradually refines. Does that make sense? I don't know.
So I mean, I think I'm sort of semi-aware of those methods. I think, like you said, I think it involves inverting sort of a system that's N by NT or something. So I think they're quite expensive, but
so it basically it's kind of like a good example because it works really well with periodic problems where you obviously move it back around again, and then a single grid which represents a whole time history. And it's a steady solution on that grid, but it represents another steady thing because it's 4D instead of 3D this time. Yeah, I just wonder if you can do the same thing.
Yeah, I mean, yeah, I'll have a look into it. Is sort of stuff I'd seen before. Like so, so this looked like multiple parallel in time strategy. Parallel is probably the most popular. But yeah.
One of the other things to do is you can make the cells different sizes, which corresponds to different real time steps everywhere. So if you time accurate, you can a looping vary real time step everywhere. It's quite useful. Yeah, it's not very advanced. That's the push for it. I was going to the simulations you had with the block of water hitting the racks. Did you do that?
These ones.
Yeah.
Let's see if it goes clear. Yeah.
So trees on the
left. So yeah, so I didn't generate this data set, it's just a publicly available one. You can see there's obviously some issues with it in the corner, even on the two side. So yeah, so I'd like to generate my own data set with a solver that I'm more familiar with. But I mean, so I would expect, so because SPH is chaotic at the particle level, I'd expect sort of any error to sort of build up and sort of pollute everything. So I'm sort of semi-surprised that at least qualitatively looks similar.
It's quite impressive.
Yeah, it doesn't take into account any sort of hydrodynamics. So this is positions and velocities to get accelerations. So there's some work to be done there as well.
I think I managed to answer that question. So. Yeah. Right. Is that it? Anyone else? Okay. And thank you very much. Yeah.